As you probably noticed, the battery died on me in a very suspenseful way, with me just asking, have I achieved what I wanted? So, have I achieved what I wanted? What was it that I wanted? I wanted to express alpha to the d plus 1 just by using powers of alpha less than or equal to d minus 1. So, have I achieved what I wanted? No, I haven't, because I still have a power of alpha to the d here. So what can I do to get rid of that? I can use my star again, where I expressed alpha to the d by powers of lower degree. So use star again. And I get minus a d minus 1. And then I plug in this entire expression there. Minus a d minus 1 alpha to the d minus 1 minus dot 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 minus a1 alpha minus a0, right? That whole thing is alpha to the d. And the rest of the terms I'm okay with, because they involve only powers that are less than or equal to d minus 1. Okay, I'm not going to distribute this and reorder the terms. You see that now the coefficients are all in f, and the powers of alpha that I use are all of degree less than or equal than d minus 1. So I have expressed alpha to the d by using elements of degree less than or equal to than d minus 1. And then I have also expressed d plus 1 by using elements whose powers only involve terms up to degree d minus 1. So doing this, continuing like this, I can actually express all the powers like this. So in a similar way, we can also express alpha to the d plus 2, alpha to the d plus 3, etc. by 1 alpha to the d minus 1. So, in conclusion, every element of F alpha can be written as an F linear combination of 1 alpha all the way to alpha d minus 1. So this set spans f of alpha as a vector space over f. Okay, so this proves that f of alpha spans, that this set spans f of alpha as a vector space over f. What remains to be proven is that it's linearly independent. We will now show that the set is linearly independent. Over f. What does it mean to be linearly independent? That means if I write any f linear combination of it that equals to 0, all the coefficients must equal to 0. Suppose alpha 1 or alpha 0 times 1 plus I should maybe use alpha a0 or maybe b0 times 1 plus b1 alpha plus dot 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 b d minus 1 alpha to the d minus 1 is equal to 0 for some b0 through bd minus 1 in F. Assume that at least one of the bi's is not 0. I mean, if they're all 0, then we're already done. That's what we're trying to prove, that they are all 0. So suppose that one of them is non-zero. So let n be the smallest, the largest. Integer in the set 0, 1 through d minus 1 such that bn is non-zero. Okay, so maybe bd minus 1 is 0. Maybe bd minus 2 is 0. But eventually one of them is non-zero, so I take n to be the largest such. Then we get that b0 plus b1 alpha plus dot 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 bn alpha to the n is 0. Right, I'm just rewriting that, but I'm only going up to n because everything above n is 0. So I can divide by bn because bn is non-zero. So b0 divided by bn plus b1 divided by bn alpha plus dot 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 plus alpha to the n is 0. So what have I found? I found a polynomial with coefficients